Start recording. All right. So far we have discussed the architecture of Spark, the need of Spark, and how to create an RDD, manipulate it. What is an RDD? We have understood that in detail. All right. Then we talked about key value RDDs earlier, yesterday, and before that we talked about usual RDDs. All right. So today we are going to, and we also tried to we tried to show an example of how do you generally convert a problem into distributed. Okay, how do you try to solve a problem by the way of distribution, right? We talked about two different problems yesterday. One, we talked about average problem, and we also talked about one more problem. There was one more problem that I discussed. All right. So now let's move ahead and explore the other features of Spark. Then we will, once we are through with the Spark discussions, we would like to do a hands-on on Spark streaming. And then we will do the machine learning part and the R and Spark SQL part. Okay, Spark SQL and R, the two things which we will discuss later. Good. All right. All right. So there were, let me just start creating the notes. And all right. These are my notes. So what's the date today? It's 18th December. All right. Good. Good. So the recording is started, and so we were discussing about the common supported file formats, right? And the commonly supported file formats are text file, JSON file, CSV files, sequence file, protocol buffers, and object files. All right. So this one we had discussed yesterday that there are two ways to load plain text file. One is using, first one is the case here where we are trying to load the data from a file or a list of files such that every line is a record of RDD. The whole file is loaded as the whole RDD such that each line is part of is a record. Okay, let me rephrase. What does it mean? In the first case, the data might be such that few lines are on one machine, few lines are on another, and some other lines are on some other machine. Okay. All right. There was one more thing which people are a little confused about. I would like to explain those parts. Okay. And with respect to the recording video, with respect to the recorded video, I have uploaded a folder in the Google Drive, which is available under on the LMS page. Okay. So here's a question to all. Okay. So question is, if you have 4-core processor and you are doing some in-memory computation, all right, you are doing some in-memory computation, let's say you are trying to do some in-memory computation. Okay. So entire thing in, all right. Now, if you have more than 4 threads, okay, let's say if you have, so those who have worked on multi-threading or multi-processors, they can answer. So how many number of parallel threads, how many number of parallel threads will be best? How many parallel threads will be best? Yes, quickly, everybody. Anup, Jin, Jitendra, Kush, Manjunath, Nada, Nitin, Omkar, Prashant, Ramana, Sapna, Saptrishi, Sheikh, Stephanie, and Thomas. So if you have four core processor, you have a single, I mean, you have four processors. 4 core means actually 4 layers of processor. So how many parallel threads will be the best? Yeah, 16, 8. Why 8? So 4 core processor means you have 4 processors. Effectively, you have 4 processors. Dual core means 2 processors, right? Quad core means 4 processors. Question is that will each processor run 4 threads, 2 threads best, or 1 thread best? 1, right? Best is 1 case. Because at the end of day, if if there is no wait time somewhere, let's say you were reading data from the disk, then it would make sense to have 2 threads. That while first thread is not doing anything, second thread would be doing the work. Okay. So yes. So in this case, 4 threads would be best. Yes. If you have 4 dual core processors, then it is best. Now, continuing from here, all right, continuing from here, if let's say you are running Spark on this 4 core machine. 4 core machine means quad core. Okay. If you are running Spark on this locally, it's not running in the cluster, then how many partitions would be best? Correct. Correct. So 4. And what would be default? What would be default? It would be 4 actually. All right. Default would be 4. Now that would answer why we had 2 tasks or 3 tasks while we were doing big.txt. Although big.txt was a small file and it has only a single block. Okay, it has single block, but it was on a single machine, and therefore while it created the partition, it cut it into 2 because there were 2 processors available on that machine. Make sense? So when we did big.txt word count, okay, big.txt some translation or say two upper, two lower and saved it to the disk, there were two tasks. Okay, because I think we have dual core machines. Good. Now, all right. Now let's talk a little bit more about it. And if you have 8 nodes, right? If you have 8 nodes in the cluster, each having each having dual core machines, and your file is spread into 8 blocks, 1 block per machine, then how many partitions will it create? You have 8 nodes right now, and let's say each one is dual core machine, right? So how many total processors are available to us? It's 8 into 2, 16. And the file, and your file is spread into 8 blocks such that there's 1 block per machine. How many partitions in total would be? 16, right? All right. So this is the way to understand why there is a partition. So partition is a minimal unit of parallelism. Each partition is processed in parallel. Okay. So somebody was confused. That's why I'm replying to it in general. All right. Good. All right. So you can handle comma and tab separated files very well using Spark. Okay. So rather than talking about it, I will try to demonstrate to you. So the way we handle it generally is by the way of reading one thing per line. Okay. So let's say we had a file which contained comma separated data. All right. So let's take the case of, take a case of, all right. Let's take the case of our MLlib data. So if we have to process this data here, which is located in data folder. So let me just show you this part. So let's say we have ratings.dat, right? So what you see here is it's a colon separated file. Okay, it's a colon separated file. So who will help me out with processing this file? Okay, this is the data that we want to handle, right? So first thing, what are we going to do? Yes, quickly. Let's say objective is find the like average, not average, let's say counts of each movie. So first column is the movie. Second column is the first column is the movie. Sorry, first column is the rate user ID. Okay. User ID, movie ID, and rating. Okay, this is the format. All right, is everybody in? So we are trying to see again another problem. Let's say we are again planning to find out the ratings, right? find out the ratings of each movie. The first column is user, then movie, then ratings, and the timestamp. Okay, what we want to do is how many movies are rated by each user. Okay, all right. So quickly, who can help me? Yes. So first thing we are going to do is sc dot text file, and then we're going to use this. All right, going to use this. Yes. Let's say I'm calling it in. Now, what will it do? Each record here, each record will become a line, right? Then what are we going to do? All right. So we don't need to parallelize it because sc.text file by default is creating the RDD for us. Yes. Now, right, right. So we can create the, we can break it down. We can break it down such that let's say we define a function which takes lines and returns line dot split by double colon, and then this is the, let's say, all right, this is our array. Okay, this is our array, and then it returns simply array 0th element and array first element. That's it. Sounds good to you? And then we say records equals in dot map. We pass this function. Now next, thank you, Thomas. All right, next, what are we going to do? Records. All right, I'm just going to put the usual where thingy everywhere. Yes. The next thing we're going to do is, Saptarish question is, should we return the first and second element? Yes. In case of array, the index is 0. Let me show you this part. Okay, so I'm here, and all right, next thing we are going to do is simply reduce, right? Simply say, all right, total equals to records dot reduce, and this plus this. Yes. If you wanted to count how many users have voted each movie, we could have said array 1 and array 0. Good. Manjunath? Wonderful. All right. So this is equivalent of defining some, let's say, I'm calling it sum2 x and y, and return x plus y. Okay. This is equivalent, right? So this is equal to these three lines. Anup? So we basically, all right, he's right actually. Thank you, Anup. Thank you. So here, instead of this, we could actually do one. You are right, Anup. So instead of adding, we should not be adding the movie IDs. Instead, we are just counting number of movies. So we should just print one. All right. You can fix this code and try to run it. I hope it should run. So I'll have to just change it a little bit. Okay. All right. So looks like this is working. All right. It says type mismatch. Interesting. Because we should have here, we should have converted it to int. All right. So there is a function. If let's say you have 10 here, you could say to int. Okay. So you could do to int and then that'll be it. Okay. So here we go again. Correct. It'll be reduced by key. Thank you. All right, I think, yes, you are right. So we don't need to do to int. Let it be this way. Reduce by key is the right way of doing it. I think I'm just trying to hurry up, and that's the cause of problems. All right, thank you very much. So this total is a RDD which you can take a look at. You can see that this particular user has rated 58 movies and so on. Good. We can say lookup one, and it should tell us how many movies have been rated by the user one. That way we can quickly check whether our approach is right or wrong. Okay, so we can quickly count this one, right? So we can quickly check. Yes, so you can see there are 53 movies by first user. All right, so that was our quick, the ETL and a little processing. Okay, ETL and a little processing. Good. So we can do all other kind of intelligence on top of this file by using all the operations that we have used in past. Good. All right. So moving ahead. So this was our way of parsing neither tab separated or nor comma separated. It was double colon separated. In case of tab and CSV and TSV, instead of double colon, there is slash t or comma, right? So this is what it looks like. All right. So moving ahead. Now, in this way, what we have done is we have plainly splitted the records by double column. And usually we would love to do that. Let's say there is a CSV data and we would simply run a map function, and in that map function we will split each string by comma, right? But the life is not all that simple. If you look at the Twitter data set, the project, there, there, each record, or yeah, in one of the data sets I'll show you, the data is saved in a Excel CSV format. Now, what is Excel CSV? In Excel CSV, in case the record itself contains comma, let's say somebody has stored the name Sandeep, Giri as the name itself. All right. Or let's say one of the column contains a proper English text, where there could be a proper sentence with comma, dots, and other things, right? So in such cases, when the data itself contains this delimiter, in open in the Excel CSV format, it surrounds it by double quotes, right? If you have a file, you try to save it in Excel in the form of CSV, it will basically surround the comma in the data with double quotes. Now, to handle that kind of records, it is generally difficult, right? It requires a lot more computing. Therefore, in these cases, we will just use OpenCSV. OpenCSV is a library in production for quite some time because it is in Java, so we can use it in Scala directly. And how do we use it? First, we download it from here, okay, using wget. Then once it's downloaded, rename it to something like opencsv.jar so that it looks nice. And once that's done, once you have downloaded this jar, pass it on your Spark shell command line, right? So you can pass it like this and then import that particular parser. And inside map, instead of saying split, you use this kind of code to properly parse your CSV file. Okay. So I'll share this piece of code. All right. Those who are looking for it now, they can, but it'll require a little bit more work. It won't happen right away. All right. So you can use third-party parsers to load CSV data. Similar is the case with, say, Python. Python also has an inbuilt CSV parser, which does the same thing. All right. But if each line is really huge, then this is going to be difficult. All right. So similarly, you can parse tab-separated file. Also, sequence files you can load in a very simple way. You could say sc.sequence file, give the name of the file, and while loading the file, you specify what, because sequence file contains two kind of data, right? Sequence file is nothing but a binary key value pair collection. Okay, a sequence file is a binary key value collection, right? So you have to specify what is the data type of the key and the value. Okay, this is something you will be informed upfront when you are given the data. All right. So here is a case of saving a sequence file and loading the same sequence file. All right, you can load the object files, right? You can load the object, save as well as load the object files. What is an object file? In all the programming languages, language by default provides a way to convert the class into, or convert each object into the binary data. Now, the problem with object file is nobody uses the object file, honestly. Okay. And my personal suggestion to all of you would be, do not try to use the native serialization of any of the programming languages. And you may ask why. All right. Try, if you are from Java background or C++ background, try saving the object just like into the disk and loading after the class has changed. You have changed a variable name in the class, and then you try to load the same serialized data, same object data. It'll be corrupted. And that's the reason why so many newer formats have come into play. All right. So many new formats. We'll talk about those new formats. All right. Such as protocol buffers, such as thrift format. They have come into play exactly for the same reason. Saving an object into the disk, keeping the future in mind, right? It is the most important part. Today, you have a class with some variables, right? And you saved the object. And later on, same class got upgraded. You added few more parameters into it. Now, you're trying to load the data that you saved earlier. It will fail. And that's where protocol buffers and thrift file formats come into play. Okay, take a look at these, say, protocol buffer. You will get the idea. Similar is the case with parakeet. Okay, take a look at the parakeet, thrift, and other formats. Right. Similarly, you can also load data if it is saved in the form of Hadoop, right? So there could be other providers as HBase, MongoDB. You can load and save data from any format. All right. So for example, let's say there was a file, okay, saved in the form of Hadoop. Then you can use the path. You can specify the input format class. Then the data type of key, data type of value. And if you are using a converter, right, like compression codec or something, then you can specify that and then use this command. And it got upgraded recently. Okay, it lets you use it with Hadoop 2.0. So a preferable way of dealing with Hadoop as of today is new API Hadoop file. Instead of saying sc.text file, you will say sc.new API Hadoop file. All right. All right. So again, as I was describing you, the protocol buffer kind of formats are used for saving data such that you can keep the data compatible for future versions. Okay. And the way you do is you create a different kind of class for the protocol buffers, okay, which has fields and the name, and you basically ask protocol buffers to generate the class objects for Java, maybe C++ or other things. So protocol buffers is an intermediate language, okay, intermediate class definition or object definition, in which you mark that this field is optional, this field is required, and this field is repeated, and so on, right? It's fairly fast and is used quite often. This is the example where we are trying to say that this person is a class with this is required, this is required. So these are the member variables of the class, and there is an enum type, and there is another inner class of the person, and this is address book containing many persons. So this is the protocol buffers class format. So you'll write in this format for whatever data exchange format do you need. So this protocol buffers or Parakeet. Parakeet also has a similar way. In both of these, we use this kind of format. Okay, so we define our objects in this format, then we ask protocol buffers to compile this, right? You see, protocol C, this is our source directory, and where we have created our files, this particular file, and then we are saying generate the Python code, or we might say generate C++ code or Java code, and it will create the object and use this in while loading data from the file or saving data to the file. All right. Now, the other thing that is required is when you want to save storage, when you want to do the compression. So far we have discussed how to read the data from a Hadoop file format, how to deal with protocol buffers. You can take a look at this project. All right. So we have created. Hi everyone, are you able to hear me? This is giving me a very strange error. All right, so this protocol buffer example, it generates the code and you can see that it has generated the Python code. Okay, so to understand protocol buffers, you can try these examples. All right, now the file compression is very important. Okay, so since we are dealing with huge data, that's why we need to compress the file very often. And whenever we are reading this data, we need to specify the format that we want. There has been huge research in the domain of compression, and there has been many formats. There has been many formats in which the compression is done: gzip, ljedo, bzip, zlib, snappy. And the way we judge a compression algorithm is based on two parameters. One, how fast is it, and whether it is splittable. So you can see that the formats that are useful for us in case of distributed computing or Spark, it's aljedo and bzip. Okay. Now, aljedo is splittable as well as fast while reading, while bzip is good with text. That's the next parameter, but that doesn't matter much. What matters mostly is whether it's splittable and what kind of speed do you have on this. All right, so aljedo is a very useful format, and sometimes we also use gzip by breaking down the files itself into small blocks. Okay, so we break down the actual files and then compress it. All right, but that's not very useful because we have saved it, and every time we want to process it, we need to decompress each part. All right, now if you want to use, let's say, aljedo, okay, though gzip is by default enabled, if you want to handle aljedo, what you need to do is, first you have to go to Ambari, and there you have to enable aljedo, and then let's say you convert one data into aljedo, and the way you convert it is using command called aljedop. And once you're done with that, then you specify the Hadoop aljedo jar on the either in the class path or using minus minus jars option. And inside the code, we could simply use conf.set this with this. That's it. And then we can read data from aljedo. Okay. So if you want to read from a local file, you can, instead of using hdfs colon slash slash, you can say file colon slash slash. If you want to read data from, say, network file system, NFS, instead of saying file colon slash slash, you say NFS colon slash slash. All right, that's it. So just changing the protocol actually does the magic. Similarly, all you have to do is, while reading the data, you can simply say s3n colon slash slash and set these environment variables. This is your key ID and secret access key. This is something which S3 provides you if you upload data into S3. So you just have to set these environment variables and start your Spark and then start loading data directly using this kind of format, S3n colon slash slash, then the name of the bucket and the path within the bucket. Okay, and we have also put a small blog here for using this. Okay, which demonstrates the use case there. All right. All right. So that was pretty much, you can read, essentially you can read anything. Sometimes, let's say your HDFS, the Spark is on one cluster and Hadoop is somewhere else. You can read the data by specifying HDFS, the master port and path in this manner. Master as in name node, colon, the port number, and that's it. If you don't specify port number, it tries to identify the usual port, the default port. Okay, so this is how you deal with various kinds of data. All right. Question from Manjunath is, on what basis does Spark create more than one reduce output files? Yes, who will help me with this? All right. So when we say that these are the output files, when do they occur? When we save an RDD into the disk. When we save an RDD into the disk, then right, then the files are created, which means it depends upon the RDD that is being saved. If that RDD has n number of partitions, then the output will have n number of partitions. Okay, and by default, when you do the reduce, the say reduce by key, if we do reduce by key, by default, it tries to create one partition as the output, which you can repartition using repartition command. Okay, you can repartition any RDD, and it'll repartition into those number. And then when you save it, it saves into those many files. All right. Good, great. Let's move ahead. Now, at times we would like to use shared variables. All right. And although we could always load a variable and share it either as RDD or wrap it inside the object and pass it along. Okay, if you refer a variable from your map method, that variable will be carried to all the nodes. Okay, and those are the traditional ways of sharing variable across the cluster, but those are not very efficient. There are two kinds of methods that are useful and very efficient while sharing data. One is called accumulator, another is called broadcast. Okay, so question to all: which operation is commutative and which operation is associative? So commutative is 1 or 2. If A operation B, who can help me with this? Which one is the commutative's definition and which one is associative's definition? Yes. So 2 is commutative. All right. Sum and max are commutative and associative. Correct. All right. We will come back to these while we discuss the accumulator. Okay. So what is accumulator? Accumulator is for the situations where you want to gather the statistics or some data continuously from the entire cluster. Let's say something is going on in all the applications on every partition, and you want to gather what's going on. In those cases, you create accumulator variable and you keep adding to that accumulator variable from all the partitions. And it will basically accumulate everything. So what it could be used for? One, noting down the progress, gathering the logs from all the nodes. Okay, all right. So if you want to count how many blank lines have been encountered, you could use the accumulator in the following way. You define a accumulator at the top, and then you interact with that accumulator throughout your code. All right. So accumulators are used for that kind of work. Now, here's a very important part. So accumulator basically using by the way of accumulator is a variable type, right? Accumulator is a variable type, and Spark has a special way of handling accumulators. So accumulator variables, you keep on increasing from all the nodes. You do not set the value, you do not set the value of an accumulator. Instead, you add values to it. You say that whatever is the value, increase it by 3. All right. Accumulator variables will be available to your code. Okay. And it will be available to your code in the mapper, in the reducer, and everywhere. All right. Now, if you remember our discussion of yarn, we talked about one thing called speculative work, speculative execution, right? In speculative execution, certain processes are executed multiple times. Correct? Do you remember that? In case a process has not finished yet, the same work is cloned on another machine and let it be executed at multiple places. Remember? So, so that's called speculative execution, where we execute same piece of code multiple times. Now, what would happen to the to the to the accumulator, because accumulator is being updated by all the processes that are running, and in case a process that was running right now, it has given its status and then it died, or something else happened, or parallelly primitive execution happened, speculative execution happened. All right, let me rephrase the question. So let's say your cluster, you have on your cluster you have enabled speculative execution, right? And you in your code you have these accumulators being updated continuously. Now when an accumulator is executed, the 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 value is increased, right? And if you execute a piece of code twice, the net result is going to be, yes, will you have twice the actual data? Yes. The chances are the accumulators would get messed up. The same function may run multiple times on the same data. Is everybody agreeing with it? All right. All right. So does it mean we will get wrong result? Yes, we will get wrong result in the accumulators. While in the case of action, while in case of action, the result is already there. And in case of actions, in case one action is successful, the second is not generally executed. All right. Therefore, either in case of fault tolerance or in case of primitive execution, as in the speculative execution, in both the cases, the accumulators will give you the wrong result. Therefore, accumulators should be used only in the case where you are really desperate to get the values at latest, such as showing progress, collecting the debugging information, and so on from all the nodes. All right, it should not be used. It should not be used for for the records where you cannot afford the error in the data. All right, where you cannot afford the error in the data. All right, good, good. So you can define your accumulator. You can create your own custom accumulator by extending a parent class, and that's it. All right. Next is the other broadcast variables. We will talk about other shared variable called broadcast. Let's say you have common words, a and the, of, at, is, and so on. You want to remove these common words from the word count. One way is you create a local variable and use it. The problem with this approach is that it is efficient. It is not efficient, okay? Because it sends the single variable to all the nodes again and again. Every time map function will get executed, if you have 20 maps in the sequence, every time a copy of that variable will be sent to all the nodes, and therefore it will be inefficient. All right. So in the cases where you want to share certain piece of data, you use broadcast variable. Internally, broadcast variables are used to transfer files, let's say libraries, or let's say Python files or other data files. Okay, so these are called broadcast variables. So by defining a broadcast variable, you can send the data to all the nodes. Here is an example of broadcast variable. All right. So you can create a broadcast by saying sc.broadcast, and that's it. Sometimes you want to work on per partition basis. All right. In those cases, you can use the, let's say, map partitions and others. All right. So, but be careful with the work you do, because, okay, because here what you see is we are creating a connection manager on every partition, right? So let's say what you want to do is you want to share a certain variable on all the functions inside a partition, right? You want to, let's say, open a database connection, and you don't want to open this database connection on every record. Instead, you want to do it on every partition, right? Because opening a database connection is heavy. Therefore, what you want to do is you want to handle the whole situation per partition basis. In that case, you can use map partition. And here we are using this function in which this connection manager is being used, and then rest of the process is going on. All right. So be careful in these scenarios where a particular function is you want to utilize a variable, a connection pool, kind of cache on every partition with per partition basis. Okay, in those cases you can use map partitions. All right, and sometimes you may want to handle the legacy code. In those cases, you can use the any program. Say, for example, our program here to handle, okay, to handle the processing need. Okay, let's say you have this nice R program which does something, and you don't know how to basically translate, or you don't want to translate this into Python or Scala right now. In those cases, you can use this kind of approach where you can just add this script as the to the you can add this script to the program, to the, you can say sc.add file means this file will be taken to all the nodes, and while calling you can simply call pipe inputs.pipe, as in this is a way in Python to execute any program. All right, and the other way could have been, a similar thing could have been done using Scala. All you have to do is use system commands to call this file. Note that this file will be copied on every node in the same folder, in the same temporary folder from which your program is running. So this file will be available in the current folder. Okay, this approach is very similar to Hadoop streaming. So you can handle the legacy code. All right. It, Spark provides you various kinds of legacy uh, statistics functions, such as counting, computing the mean, okay, computing the sum, computing the max, min, variance, sample variance, standard deviation, and sample standard deviation. Okay, so you could generally call this way. Okay, I'm not sure if it works with Scala. Let's try to do this. Will it work? All right. All right, let's just check. It does. Yes. So standard deviation it has given us. So A dot is working fine. Similarly, A dot mean should work fine. For some reason, it doesn't autocomplete. Okay. So there are all kinds of functions. The general summary statistics are available like here. So you can see that, let's say you want to quickly take a look at the variance. All right. Okay. So these are the standard functions that you could use. All right. Let's say you are trying to identify an outlier. So you can simply compute the mean first. Okay. And using a map filter, you can find out whose value is 3 standard deviation away from the mean. And that's what we have done here. Math.fabs is, all right, math.abs, does it work? Yes, right. Good. So you can use this kind of similar approach in case of scalar for computing the outliers. All right. So most of these parts actually we have covered earlier. It's just running through it once more. All right. Good. Good. Moving ahead. Any questions till the point? So these two topics, I would like to keep it a little brief. I want to spend more time on the Spark streaming, okay? Because these parts are something which we have been discussing so till now. All right. So we have already discussed that on every machine there is a worker that gets executed, and the same thing is true whether it's Mesos, Yarn, or standalone. Okay, standalone means that there is no third party external resource manager. It is the Spark's default resource manager. All right. So driver asks the cluster manager or Mesos, Yarn, or standalone to get the work done, and it gets work done on the node. All right. So the driver is somebody where the main method is launched. Okay. When you launch a Spark shell, you have created a driver program. Once the driver terminates, the application is finished. While running, it performs the following. It converts the user program into tasks, right? And how does it do that? First, let's say whenever we said rdd.take, it would figure out, it will basically figure out all the units of execution. It basically would try to create a directed acyclic graph and then figure out what are the things that could be done together or separately, and based on that it will create a physical execution program, and then it'll schedule those tasks. Task is basically multiple operations, or maybe it would break down single operation into multiple. All right. So task is something which has to be done together on the executor. All right. If you have a.map, b.map, both of those will go into the same task. All right. So so the driver does a lot of heavyweight lifting. One, understanding your program. Second, launching it on the Spark. And then once it is terminated, then it shuts down everything. then driver also coordinate with the resource manager in scheduling the individual task. Okay, so it schedules tasks based on data placement by coordinating with the resource manager again, and it tracks the cached data which is there on every machine. When we say rdd.cache, driver makes a note of it that this piece of data is cached, all right, and tracks cache data and uses it to schedule future tasks. Okay, and it also starts the Spark's web interface at 4040 port. But if 4040 port is not available, it will try on 41, then 42, then 43, 4041, 4042, 4043, and so on, right? So now this is the work done by the driver. Okay, so driver is the main coordinator, and executors execute the task. Okay, the worker processes, executors are the worker processes that run tasks of a job, return result to the driver, and these are launched once at the beginning of Spark application. Okay, and they run for the entire time of the execution of application which they are running. All right, and they provide in-memory storage for cached RDD via block manager, and in local mode driver and executors are from same process. Okay, okay, so going back to the diagram, so you have three kind of things here. One is Spark driver that for me is running, my shell is running on e.cloudxlab. Cluster manager in our case is the yarn. Okay, third one is each individual node which are participating in the Spark execution. All right, so we have talked about two parts: one, the role of a driver, role of an executor, and role of a cluster manager. Although it's very clear to us who does what, but we just want to make it a little more details. We just want to give you little more details. Okay, so cluster manager is the one who makes sure that executors are executed. Whether in case of Yarn, they are executed by the node manager, right? In case of Mesos, they will be executed by somebody else, but is the sole duty of the cluster manager. And this component is pluggable in Spark. It allows Spark to run on Yarn, Mesos, and or if nothing is available using the built-in standalone. And this is what happens. When you as a user submit the program using Spark Submit, or you say Spark Shell, there you execute an action. This is what happens. You call a command called Spark Submit that creates a driver, and then that Spark Submit may be calling another driver, and then driver is talking to cluster manager. Cluster manager starts the execution and then finishes. Okay, and right. So we have already talked about this part where you can submit to the cluster. You can simply say Spark Submit and then pass the argument and submit it. All right. Now we have already talked about what does it master means, deployment mode means, class and name and jars. Okay, so if you have many files, let's say you're doing the CSV parsing, so you can hand over your jar by mentioning spark submit dash jars, and pass on all the jars, say open csv.jar into the command, and these jars will be copied on every node and will be used, the classes will be used in your program. All right, same is the case with Python files. All right. So we've actually talked about all of this. We'll basically bundle all the libraries using SBT. All right. And then in case you are using your own Spark installation, you can explicitly mention that this is the location of our Hadoop so that it discovers where is the resource manager and name node, and it'll basically interact with the other variables, these two other variables, where we are reading, where we are setting up the AWS login password. All right. Similar is the case with Apache Mesos, and similar is the case with standalone cluster. In case of standalone cluster, you have to first do the entire installation of Spark on all the nodes and get it executed. Now, a bigger question that we need to answer generally is, which cluster manager do we use? Okay, which cluster manager do we use? Thumb rule is, I mean, it sounds very lame, and uh, in one of the interviews where I was interviewing for a junior position, and I asked a candidate that would you use inheritance or you would use composition? Okay, will you extend, or the question was, will you extend or implement? Something of that sort, right? In this interview, it was about object-oriented programming, and I was waiting. I think, let me recollect. Question was whether to use interface in Java or should we use abstract class. All right, and you will be surprised by the answer. The answer I got was, whatever my boss tells me to do. I'll I'll use the interface or abstract class. I'll do whatever. All right. Although for non-computing job, this kind of answer is great, right? But in the computing job, I would be expecting him from like the reasoning behind why would you choose abstract class or the interface. All right, so I hope you got the joke. All right, yes, yes, Anup. And yeah, so of course he did not get a job, and because yes, it depends on the scenario. That's also a good answer. So I'll ask him. My further question would be, if somebody says that depends on the scenario, that I'll ask him, like, explain to me two scenarios, one in which you will need interface, other in which need the abstract class. Okay, and that's where I would try to understand his understanding of the computing. All right. So, I mean, there's a general style of interviewing where you basically ask a very superficial question and then you dig deeper. Okay, good, good. So yes, Manjunath, you are selected. Right. Yeah. Okay. So now coming back to the cluster manager, my answer is the my answer is that you do whatever your boss tells you to do. Okay, so you start. So the general thumb rule with cluster manager is you first check with the organization, like, are we using Hadoop already? Do we want to launch our stuff on the Hadoop already, or the organization has no installation at all, or are they using Mesos? So that's the thumb rule to live by. In case the organization doesn't have any, then in case the organization doesn't have any, then you use standalone, or maybe you suggest that why don't you have a proper Hadoop installation rather than anything. In all cases, the other thing, what people do is they start with standalone cluster if it's a new deployment, And if it's not, if you want to have a richer scheduling capabilities, then you use yarn and mesos. And if if your user base is humongous, if you have, say, 10,000 users going to share the same cluster, then mesos does a better job than yarn. Okay. So, I mean, there's always this argument about whether to use yarn or mesos in the organization. The default is that use yarn because there is a lot of support on yarn, right? For example, HBase runs on yarn but doesn't run on mesos, right? But in the extreme cases where you have 10,000 users who are going to share the same cluster, in those cases, you install mesos, right? So that was a quick overview of running in on the cluster, right? Second one also, I'm going to give you a very general idea. All right. So while we, you know, while we execute our program, either from the shell or let's say do the Spark Summit, we can provide the configuration in two formats. One, on the command line argument, other by setting up conf object like this. By using the Spark conf object, we can set various values, okay? Or we can pass on the command line, right? By specifying various arguments. So either one is fine. While first one needs you to code it in a file, second one is just an argument. Okay, and there are many configuration variables. There are many configuration variables that you can use to fine tune. First one is the executor memory. How much executor memory do you want to set? Okay, so generally you keep it at a lower side. In case your individual machine is really high end, then you increase this memory. All right. All right. Sometimes you may want to enforce number of cores on every machine. Sometimes you want to turn on or off the speculation. If you turn on the speculation, the accumulators might go haywire, but it might finish the work faster by making the cluster more busy. Okay. Then, right? Then how much time is okay for you? Okay. How much time is okay for you to keep the executors alive, right? How much time is okay? In how much time do you assume that the executor is dead? All right. And in case your program needs some more Java options, you can pass there. And if you have extra class path, you can pass here. And if you have extra library path, then you can pass it there. Okay, we have already talked about a little bit into tasks and jobs and stages, but let's go through this. Okay, although this piece of code is in Python, but it should not be too confusing to us. Okay, let's try to do the same thing here. All right. So you can see that it has got these details in place, right? And let's try to do some more things. I'm going to say this, and now you can see that by default it created two partitions. This first variable is a two partitions, okay? And here it created 10 partitions. Here because we explicitly mentioned the number of partitions here, right? And here you can see the entire detail about what's going on where. Correct? Let me see if I could a dot. All right. A is just a parallelized collection with 4 partitions. Why did it have 4 partitions, by the way? Okay, maybe it's on the current node and current node has quad core. All right. Now, let's say we create a flat map. Let me convert this piece of code into into Scala. All right. So we are saying yes. So proc CPU info is a general command. Okay. So the slash proc is a folder in Unix where information about all the processes that are running is kept. Okay. So we could simply say underscore split. All right. Now, when we say words dot to debug string, you can see this. So for this, basically, when you say debug string, it shows you the chain. Okay, it shows you the chain. And let's say we go one more step ahead and create this words dot map, and we are returning, let's say W. All right. Okay. All right. Now you can see clearly that first we did text file, then flat map, then map, right? So it shows you the entire process, entire chain of commands. And if we say reduce by key here, all right, let me just say reduce by key and reduce by key, and we are saying this plus this. All right. Let's take a look at reduce by key. Now result dot to debug string. All right. So here first text file, then flat map, then map, and reduce by key is a shuffled RDD. So you can see that in this entire process is going to be in a single task. You can see that when you have everything on the same level. It's the same RDD. There's basically going to be same task. But when you say reduce by key, there's going to be shuffling, and it is going to shuffle and execute it as a separate task. Yes? All right. Or they call it stage actually. In simple words, it is a stage. So you have RDD graph. First we have Hadoop RDD, then we did map, then again map, then did with some filtering, and then shuffled. So all of these things are going to get clubbed together, right? These are going to get clubbed together, and then they're called one stage, another stage. Okay, so your RDD graph is going to get broken into stages. Any questions so far? All right. So user defines a code in a directed acyclic graph manner, as I showed you just now. Then action forces the translation of DAG into execution plan, and then tasks are scheduled and executed on the cluster. Okay. You can take the information from the Spark UI. Okay. And how do you go to UI? By locating the port number first. First, let's locate the port number. When it got executed in the beginning, okay, when we executed in the beginning, we'll have to locate the beginning of our program. When we just booted it, yes, you can see this is the, no, not really going up. Yeah. Here you can see that there are error. This error is occurring. While why? Because other people are also using Spark shell. The port get blocked, and you can see that for me it is on 4042. It started Spark UI at this. Now since it's a local IP address, it's not accessible from us. Therefore, I will use my console domain, meaning e.cloudxlab, and then the port number. Make sense to you? All right. It shows that all kinds of jobs that have been completed by me. Remember, I did take, then I also did lookup, and I also did standard deviation, mean, variance. Okay. Why does it not show me the current one? Okay, I think they are not yet finished. Oh, I haven't done take yet. The job has not been executed yet. If I say result dot take 10, then it'll be executed. Okay, so you can see here, you can see these are the active jobs. You can go into the details and take a look at it. All right, this is what's happening. Map has finished. Now take might have also finished. Yeah, the whole process is done. And there were 10 tasks earlier, okay, because we forced that to have 10 partitions, and now it's only one when we say take. All right, clear to everyone? So find out your port number, and then you open whatever is the console URL, call on the port number, and you will see the UI. Okay, it will also show you the cached data, whatever we have cached. Okay, so for example, the one which we did recently, right, the take, here is the DAG visualization. Okay, here's the DAG visualization. They're basically, All right. It doesn't show much information. Okay, shows a graph of RDD operation in this stage and RDD inside each one. All right. No, DAG does not mean that everything was run locally. Okay. DAG only means that when you type a command, it's like it's like the waiter taking the order, right? When you say that you need this, you need this. So waiter keeps on taking the order. The form in which that waiter is taking the order, that's a DAG, directed acyclic graph. So this particular waiter called Spark is little smarter. Instead of just taking the order uh, in a casual manner, it basically keeps on drawing a graph. Okay. And instead of you telling him that you need omelette, you're telling that first break the eggs, then put it on, heat it up, and then do these, do that. All right. So DAG is nothing but the form in which, so DAG exists locally on the driver, but the process is executed on the cluster. Okay. So I want to see a complicated graph. So yeah, if you look from the below, as in from the point the things get executed, in that way it'll look always like a linear, right? But if you see the entire process, your code, then from top down, then you will be able to figure out that it's a kind of a graph. All right. Because if you see here, it's looking like straight graph here, not graph as in to debug string, right? It's linear. This depends on this, depends on this, depends on this, depends on this. Good. Now coming back to it. All right. So using Spark UI, you can explore the other variables like what what is your execution environment and how many executors have been allocated and the was there an SQL executed or not. Okay. When we do SQL, then you'll be able to see that part. All right. Okay. So let's take a break for 10 minutes. All right. So should we start now? We are 2 minutes past. Is everyone back? Anup, Barsa, Jen, Karthik, Kush, Manjunath, Nada, Nitin, Omkar, Prashant, Priya, Ramna, Sapna, Saptrishi, Seek, Stephanie, Sundar, Tad, and Thomas. Great. So looks like everybody's back. Let's start. So using this UI, you can are you able to see my screen moving or is it frozen? Is it frozen or you can see the screen moving? All right. Good. All right. So you can see the details of the entire process using the web UI. And if you exit the console, this web UI will die. Okay. Now, so another question that is there, where do I see the logs? Okay. So the logs are generally handed over to Yarn. Therefore, you can use the Yarn to take a look at the logs. And how do you do that? If you go here and take a look at the job browser, okay, and here anything which we run there using Spark Summit should come here. All right. All right. These are the things I ran later on. And Spark by, okay, nothing from today. All right. In the standalone. All right. In this, basically, we can take a look at the logs using Yarn. Let's try to locate the logs. And the application ID. So when we executed a task, right, there would be an application ID. Okay, let me just try to locate. So this was one job that completed. Okay, and let me just see. All right. So looks like it is all right. It's not creating the app ID usually. When you do the Spark Summit, it does create it. Okay. Is it running in the local mode? I see. I see. It looks like it's running in the local mode. It's not running on the cluster. Yeah. So far, it has not run on the cluster. All right. Hmm. The application name is Spark Shell. And what is the container? All right. Looks like this one is running in the cluster mode. But if you do the Spark Summit, it generally goes there. Also, we can change that by launching Spark Shell again and specifying master as something else. All right. So, but in general, you can either use this job browser to see the logs of your executor, or you can use yarn logs command. Okay. The key performance considerations are number one, labels of parallelism. What serialization format are we using? Okay. Labels of parallelism is dictated by who? Quickly. Yes. Anyone? Yes. Number of partitions. Correct, Prasant. So processors dictate number of partitions as well as your data distribution. And yes. Okay, great. The second thing is serialization format. Serialization format is something you cannot change. That is something, the input data you get. Third is memory management. Okay, memory management is something up to you, how you break down the work onto the RDD in case you try to read the entire thing. Okay. Fourth is the hardware management. All right. So by default, there is a single task per partition, a single core in a cluster to execute. A good degree of parallelism is based on underlying storage and the processor. Okay. And in case of HDFS, there will be one partition per block, provided there is single processor. Okay. If you keep more partitions, then there'll be some overhead because the data might get transferred to other nodes in case you are enforcing partitions. If there are too few partitions, the few resources will be too stressed out, other will be too idle, and the overall time might go lower. Okay, so there are many ways to control the parallelism. One, while loading the data. Second, after the shuffling parameters, almost all the shuffling parameters, such as shuffling functions, such as sort by, reduce by, most of them take the partitions in the output as one of the arguments. If not, let's say you want to repartition things, you can use the command called repartition. It will repartition the data based on the key in the tuples. Okay. Sometimes when you execute a lot of commands, uh, in a larger process, sometimes you might have to shrink the RDD because of the filter or other processes. They, you can achieve a better output by repartitioning or coalescing. Okay. Say, for example, there were a million records spread across, say, 100 partitions, or let's say spread across 50 partitions. And after the filter, you are left with very few records. So you don't need those many partitions. What is advisable is repartition in such cases where after filtering or after other operations, only a small data is left. Okay. So this is the example that I've quoted just now. All right. You can repartition the data. All right. So here is one real good example for all of you to take a look. In the first case, what we did was we loaded the text file, counted the number of partitions, and then we filtered based on this command, based on a vector called this, as in if the records are starting with a line with a word called this, only keep those lines and then remove others. Okay. So so the RDD1 will have very few words left. Okay. So when you say RDD1.count, it's going to take more time than the second one where we have repartitioned and made only single partition after this. Okay. This saves a lot of time. Can you see the difference? In the first case, the time is around 1.5 seconds, while in the second case, the time is around 1.1 seconds. So there is a 40% differential. Why? Because after this filter, only few lines will be left, and still the partitions will be 2. Therefore, it's better to repartition or coalesce to bring all the records to 1. All right. So serialization format, while transferring or saving object, we need serialization, and it comes into play when during either transfers or saving to the disk. By default, Spark uses Java's built-in serializers. Now here is a benchmark, and out of this benchmark, proto stuff, which is protocol buffers, and cryo is giving very great results. All right. So there has been a lot of work and a lot of research on these serializations, and out of that, protocol buffer and cryo seems to be winning. All right. So it's a serialization format is supported by Spark, and basically just like JSON, XML, and others, it has these are also format of converting a complex object into sequence of bytes. Okay. So we have already talked about it. So I mean, you can cache the results, you can shuffle and aggregate buffers. Okay. Now, a big question which people ask me is, how is the memory organized, right? How much memory does Spark consume? Okay. A lot of us feel that it basically, whenever we are reading data from HDFS or anywhere, it's going to consume the entire RAM. It is not so. Let's try to understand it. So the way the memory is organized is the data that gets consumed is 60% of the total memory allocated to the executor. On every node, the RDD storage at any point of time cannot go beyond 60% by default. 60% of the total memory on uh, on every node, 60% of the allocated memory, total allocated memory to the executor. If this limit is exceeding, what and this happens temporarily while doing the processing, only during those time this data is kept if the cache is not called. All right. While shuffling and aggregating, if you remember, when we shuffle something, order something, we create temporary variables. That takes around 20% of the by default, 20% of the memory is allocated to that. And 20% of the memory is allocated for the user's code, because whatever jars you are using, whatever code you have written, that gets loaded into the memory, and we call it permgen memory in case of virtual machine. And this memory is around 20% of the total memory allocated to the executor. Okay, so on every machine there is an executor running inside the container. We allocate some memory to this executor, and it should not be more than what has been specified in the containers. And out of this executor's memory, 20% goes to code, 20% for the temporary buffers while sorting and other shuffling, and rest 60% goes to RDD operations. All right. So, so in case of Spark, hardware resources give a decent significant effect. Meaning, if you have better hardware, Spark is going to perform better. Why? It automatically figures out that you have so many cores, so it's okay to create so many partitions and so on. So it automatically does the parallelization between all the threads. And similarly, it also consumes the memory accordingly. Okay, so the amount of memory that you give to each executor, the number of cores of each executor, number of executors, total number of executors, which is a function of total number of machines, and number of disks for intermediate shuffling data. Okay, and the memory that you set in the executor. And generally, as a thumb rule, the application benefits more memory than cores. Okay, how many of you agree with this statement? It's a very general statement. The application benefits from more memory than cores. Like for example, if you have a slow laptop, older slow laptop, if you increase its memory, the chances are it will start going faster than replacing its processor. Okay, so Spark has got the linear scaling. Linear scaling is a very important criteria in distributed computing, meaning if you increase twice the resources, do you get twice the performance? In case of Spark, that is true. Okay, but remember, in case of Java virtual machine, if you have too much of memory, say 200 gigabyte of memory and plus more than that, there'll be more memory to clear up for JVM, and therefore there could be garbage collection pauses. Okay, so basically it makes sense to have 60 GB or less kind of memory per executor. Right, so that was about a little optimization. Now what we're going to discuss is a very important. Okay, very important, although in general you may not need to optimize the cluster, but what we're going to discuss is a very important topic. All right, I'm sure everybody has gone to sleep by now. Okay, so if you want to go and wash your face or drink some water. All right, so this is something very important. This is something which requires a little different kind of thought process. So far we have tried to learn something which neither of us are trained with, nor most of the systems that we have learned uh, use that. And so far we have tried to learn how to do something in parallel. Okay, human doesn't do things in parallel. We can only write one thing at a time. We can speak only one thing at a time. So it's very difficult to do. Mostly even debug the code which is having many threads or running in distributed way. Okay, so that's why distributed computing or parallel computing sometimes gets little harder. Okay, but thanks to these frameworks, they have made our life easier, and they have made it uh, quite usable as of now. All right, the systems like Hive, systems like the filters and maps that we have run, and Spark SQL, they have made the distributed computing really simple and obvious. Okay, so we learned that part. Now there's another thing, and this thing, although we see this kind of work all the time, but we generally don't deal with it in our normal computing. So the idea is about streaming. What does it mean by streaming? Okay, streaming is a very important concept, as in, although the word is being misused while watching the movie, we call it streaming, and while running the program, running the command line, we call streaming. And here, the streaming means processing continuous data. Okay, what does it mean by processing continuous data? It means in case the data is not coming, the program will wait. Okay, the program will wait for the data to come. Okay, and 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 it's not somebody is executing or somebody is running the program. It's the way the program is designed. The program is designed in a way that it continuously consumes and produces output. It continuously runs, keeps on consuming data, and keeps on producing data. All right, now question is, how do you test such kind of application? Anybody? How do you test continuously running processes? The way you test these kind of processes is by putting kind of a poison in the input, and as soon as your program notices a poison in the input, it would stop the job. Okay, and that's how we generally deal with testing of continuous data. Because if you think about it, imagine that there are multiple programs running continuously and consuming the data from each other. Okay, so let me try to draw it. Okay, let me try to draw it. All right, let's imagine that there is one queue, another queue. Okay, so and generally whenever we deal with continuous data, we generally create these nice queues. Okay, so on one end, you keep on pushing data to it. You keep pushing data to it. On other end, the program will consume it. Okay, let's just denote the program with kind of, how should I denote the program? Okay, let's just denote the program by a rectangle like this. So this is our program. Doesn't look great. All right, so let me just make it like this. Okay, now this program keeps on pushing data to this queue. On the other hand, somebody else would be consuming data. Okay, so from here, your data is kind of coming in this way and you're processing it. And let's say you are converting it into kind of thinner this kind of slices. Okay, and yeah. So this you can think of like this program which is continuously running indefinitely. If this queue is empty, it'll wait for this to process. And if it is full, the producers here will wait till it makes some space. Similarly, this side, this program will wait, whosoever is on this side will wait if there is nothing inside, okay, and so on, right? So this is the typical way of handling it. Now these queues that you see in this diagram could be Kafka, Flume, HDFS, or maybe from Twitter. This data could be coming from Twitter, or this queue could be your Kafka, and this queue this queue could be, let's say, some other queue, say Flume or 0MQ. Okay, and this program here is your program. Okay, this is your Spark Scala program. Okay, now as you would notice that this program, since it keeps running and keeps on processing, all it does is it consumes multiple packets and then converts it into some output. And basically it takes these packets from it, converts that, loads that into an RDD, runs your script on the RDD, and then whatever is the result of your script, it gives either to the std out or saves it somewhere. Okay, so this process keeps on going indefinitely. In case Now, since this program keeps running, in case you want to test it, and let's say you come up with a plan that you will kill it. So if you kill it, then some records might be lying here, right? And those records might keep lying and your process has been killed. So let's say you put 10 records here and you were expecting 15 records here as part of testing. And let's say you put 10 record this side and you were expecting, say, 50 records from this side, right? But since as you killed it after putting 10 records and waiting for some time, some of the records might be lying here, and therefore therefore the process is not yet completed. Okay, so the only way to test it is that you come up with the idea called poison, and the poison, your program which processes it should understand the poison means just shut down and put the poison further here so that the other programs understand the poison. Okay, most of the parallel computing languages such as Golang, they basically come up with the idea of, I mean, they don't provide threads, but they provide parallel computing by the way of queues. Okay, and they provide the poison as well. Now coming back to it, so what you see here is It's a typical producer consumer. On this side, the producers are producing at their own pace, right? On the other side, the consumers are consuming it. It's like your belt, the conveyor belt. The queue is like a conveyor belt. And okay, so this way of parallelism, even outside the distributed computing, this way of parallelism using queues is very powerful. Therefore, this queues or event bus, they are also used as event bus in an organization. Okay, they're also used as event bus, and 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 on one end the events are being pumped, and other end there are listeners who are listening to the events. So even before distributed computing, the idea of a queue which was organization wide became very popular. Okay, because it made it possible that programs of two different parties could respond to each other by the way of queues. Okay, so it provides a standard producer consumer phenomena. All right, does it make sense to you? Right. So one of the works that I worked at Amazon was to build this kind of a streaming engine. There, my predecessors were using the threads to solve a distributed computing problem, and threads became messy, and there was no way to solve that kind of distributed complex parallel work, because this diagram looks simple. This is somewhere our brain can kind of understand it. But when threads come into picture, it doesn't it doesn't kind of fit in. Okay. And and basically, if you have like 30 of such processes running and you try to draw them and try to think about threads, it further complicates. So most of the thread kind of problems can also be very well solved by queues. And such queues are generally called blocking queues. Blocking queues means they block you if they are full, they block the producer when they're full, they block the consumer when they're empty. Those are blocking queues. All right. So streaming is a way of consuming data, and there are many other streaming engine. One of those is Storm, and even Kafka has come up with their own engine now. All right. So Spark Streaming is most powerful because Spark Streaming is heavily distributed, and it provides you all the construct which Spark provides. Okay. So the way Spark Streaming works is very, very simple. The way it works is there is a continuous loop. This continuous loop keeps on creating RDD and executing your code against the RDDs. Okay, it keeps on executing the code against this temporary RDD. So it basically consumes data based on the time window and converts that data of like 1 second, 2 seconds into the batches, and then runs your Spark code on that batch converted into RDD. Okay, and whatever is the result is further processed or saved based on what you want to do. All right, so this is how it looks like. Internally, this is what happens. On one end, data is coming in. Data from 0th second to 1 second would create first RDD, and then another RDD, then another RDD, and against each of these RDD, your code is being executed. All right, your code gets executed against every second's RDD. So this RDD has been created on a time window of 1 second. You can create an RDD based on say 2 seconds, 3 seconds, or 10 seconds, or whatever you want. All right. So On top of it, Spark Streaming also provides you a way to club multiple D streams or temporary IDs. We call them D streams, by the way. This is a D stream, this is a D stream, and so on. So you can perform further operations on these RDD. You can club them together by creating window on top of them. All right, let's try to solve it. Let's try to understand it. Let's first of all create a connection to the service. Okay, first of all, what we are going to do is we are going to turn off the errors. We are going to only turn on the errors on the screen so that not too much text is shown to us. Okay, so the very simple way of doing that is by setting this label to error. Okay, so you can see that if I set this as error, now if I execute some old command, the whole thing that used to scroll is gone. Okay, so you can also try it, right? So we are trying to, the first thing we do is we basically create a connection service. What does it do? It imports the streaming library. Second, it talks to the, it creates this SSE context. The way we have SC, which is Spark context, we have Spark streaming context. And here we are saying that this is Spark streaming context is going to be based on 1 second. Okay, whatever input it consume, it will convert the incoming data, or it will club all of that data into by 1 second. For a whole 1 second, it will keep on consuming and create an RDD out of it. This is what it means. Now, the next is specifying where should the data come. Here we are saying that socket text stream, meaning connect to this port, this host at this port and consume the data. Sounds good to you? And then, and then, and then we will, once we have created these lines is not an RDD, it's called D stream. It's kind of a wrapper. Whatever code you are writing, this code is going to get executed on every temporary RDD, which will get created in future when you submit the program. Right now, we are basically working against this particular D stream. So lines is a D stream which will be based on 1 second's window after connecting to this particular host. Okay, and then we are saying this lines, which is a D stream, behaves very much similar to what RDD behaves, because it's like a temporary variable representing the future RDD. So here we are saying lines.flatMap, then words.map, exactly the similar code that we have done earlier, and then print. Sounds good? So we first opened the connection, then we created the word count for that particular window, 1 second window. This will be executed on every 1 second, data received every 1 second. And then it will print the results. Okay, every second it will print the results. Now, third is we create the dummy data producer, because it is going to connect somewhere and consume data. And how do you do that? By using a very easy command called nc-l. Okay, nc-l. Okay, and once you are done with this, then you will say start, let this magic begin. And once that magic has begun, it'll keep on consuming the data continuously and then wait for the termination. All right, let me try to do this right away. Okay, let's try to create this. I'll create two terminal. Let me close the first one. Okay, I have one terminal here and there is another terminal. Okay, so the first two terminals, in the first one I have Scala uh, prompt open and we are going to execute this. All right, so we have defined lines. Let's take a look at lines. Okay, it's a D stream, it's not an RDD, although it has all the methods that D streams provide. Okay, are you also doing it with me? Yes. All right, now let me write the code here. All right, let me pass the code, same code here. All right, so now we have written a program which will be executed every second. Okay, as soon as we start the magic. Now on the second terminal, I'm going to open this. Please note that for you, you have to choose some other port. Okay, I have chosen this. You choose some other port. Okay, some other port below above 1024. Okay, so you can choose 9998 and declare it to others because they might be using the similar one. So that you don't read each other's data. So right now in this example, on one end, using NC, we are producing data, and from there, our Spark streaming is consuming data. So this guy is speaking, and SS has connected to NC. Here we will be speaking to NC, and NC will be giving the results. Okay, NC is nothing but whatever we type here, it's going to give it to anybody who comes and connect on this port, on this service. Okay, that's what happens with NC. All right, Prasant is using 9995. Okay, anybody else? Omkar is using 9994. Thomas. So on one hand, in the first terminal, we're going to consume data, and in the second terminal, I'm going to produce data. So have you written the consumer? So first one is the consumer, which is Spark streaming, and the second one is going to be producer. And what will it do? After it has completed the word count, it will print those. All right. So it will print the word count in every second. Okay. Everybody set? So this is the command that you are going to execute in the second terminal. First, whatever you have to type in first terminal, I have already given to you. Okay. And yes. So all we did was first turn off the too much of text from the screen, imported streaming everything from this package. Okay. And then we created the context, streaming context, and over the streaming context, we opened as we are trying to create a socket stream to this particular host. And then lines will contain the lines per second that are coming in. Then we convert it into words, then pairs, then do the counts, and then print the counts. Okay? Now let's start the magic. Let's go back to the first terminal and we say start. We say start. All right. Now you can see that it has done the computation here. Okay. In the first one, but it is not doing any more computation. I'm typing really fast. Okay. So it has done the computation. Every second it's doing the computation and printing it. All right. So let me just paste it here. Everything. Okay. Did something here and it finished the work. All right. Let me just paste it really, really fast. Really, really fast. All right. So it's doing the computation continuously. Since there is no record, it's just printing empty. Jin's question is this type of streaming only for unstructured data, but not for structured data with Scoop? With Scoop, the data is static. Tables are static, okay? Therefore, with Scoop, it's difficult to do, okay? But with Flume, this is very much possible, all right? Moreover, Spark Streaming not only lets you read from the socket, it can let you read from Kafka. It can let you read from a HDFS folder where files are being added into the folder. Okay, wonderful. Okay, so on the other hand, this is being computed. Now, let me turn off. Now it will start giving error that it is not able to connect to this. Now there is a command called yes. Yes command is for the people who are extremely lazy and they want to just agree with all the terms and conditions. So they can just say yes to all and it'll keep on printing Y on the screen forever. Okay, so yes command, let's use the yes command. If we pipe the output of yes command to NC, it's going to produce Y and give it to our Spark streaming. Now you can see this. So on one hand, we are producing this humongous data, and the other side, we are counting number of words. So you can see that we're counting around 163,000 here, and here 1,300. Okay, so you can see that. Good. Is this example clear? Is it running for you? Great, great. Now the next plan. Now let's do the same thing. Let's do the same thing. Right now we did it using the UI. Okay, so this is the same program in the Python. So this is what we can also do. All right. So this diagram shows that this guy is a listener who is consuming. So we can execute the same program using Spark Summit. So Barsa's question is, okay, I think I missed many questions. First question is from Saptrishi. Sorry, Sandeep, where do you view the consume data? Consume data is being printed this side. So if we do this, consume data is being printed here. Does it make sense? All right, the process has not started. Okay, sorry. Let me copy paste those two commands as well. The one that I did not share with you, these two commands, right? These two commands. Go to the first terminal and say ssc.start and then ssc.await termination. Okay? So who all were able to run it? Nobody? Wow. Good, good. So Seek, Jane, Thomas, Prasant. Right. So for you, you were able to see the statistics? Wonderful. Okay. So is it clear to everyone what's going on here? If somebody is stuck, I can help you. All right. Now let's All right. Now let's move ahead. We could submit the same program to the to using Spark Submit. We can submit the same program and get it done. All right. So yes, we have already talked about these parts using. All right. We don't need this. All right. So we have talked about these parts. So you can have many kind of sources, either TCP connection, you can read the data from file streams, you can create your own custom sources, you can basically queue another's RDDs as a stream, as well as you can define the custom sources. Okay, let's say you have an HDFS data directory. You can say create text stream. I mean, using the function called dot text file stream from a directory. So as in when the files are getting added into this directory, the newer files will be considered for the consumption streaming. Okay, so do not modify the data. Instead, you just keep on adding new data. All right. Now let's talk about Kafka. So Kafka is a great queue. It is basically for publisher subscriber. Publishers push the messages into Kafka. Subscribers consumes those messages from Kafka. Probably every queue in the industry can be used as event bus or publisher subscriber hub. Question from Prasant, that where should we use SSC await termination? SSC await termination makes it run forever, okay, unless it is killed. Okay, so that's a general way of execution. Anoop's question is, how do you kill it gracefully? The most graceful way of killing continuous data consumption is by either using ssc.stop. Okay, there is a function called ssc.stop. Okay, you can use that one. All right, and then it will stop. But the best way of stopping, yeah, best way of stopping it, stopping any unbounded data source, on any streaming process. That is something it took me some time to figure out, is by the way of inventing your own poison. In the source data, you put a poison, and all the processes that consume it, they will shut themselves down after consuming poison and put the poison in the next chain. So that's a general cool way of shutting down the entire process in case of unbounded data source, or in case of Spark streaming. All right, you will have to define kind of data type which is called poison and then put it. All right, so yeah, yeah. So it should stop. All right, so I have kind of pressed Control C. I wasn't sure if, okay, yeah. The poison can shut down the streaming, but the queue is still active. Not really. The queues are forever running programs. Okay. So for example, that one I'm talking about, Kafka. Kafka runs for the whole organization. Kafka doesn't run only for you. Okay. So you don't generally kill the queues. Kafka is distributed in the sense that Kafka runs on many machines parallelly. It is partitioned, as in some of the messages would be on some machines and so on. It is replicated, commit log service. Okay, to run streaming and Kafka, these are the things we require: Zookeeper, Kafka, Spark, and the good news is these are all installed by HDP, Hadoop Data Platform. Okay, you might have to download the Kafka library to use with Spark and Scala, and that we have already kept it in Data Spark. A question from Saptrisi: is publisher subscriber same as event bus? Yes. Okay, so event buses are used for publisher subscriber or event systems. All right, so I've already committed the code at this place. If you want, you must have cloned it already. Let me exit from here and go into this folder. Oh, it's not there. Right. Once you have pulled it, you can go to that folder and, sorry, once you have cloned it, you can go to the folder and pull again. All right. So I have here one folder called Spark Streaming. All right. So here there is build.sbt, right? Here we are saying that the library that we require, and we are saying that we require streaming and streaming Kafka library. Okay, and the program that we have written is this. Is it clear to everyone? Here we are saying that we are going to run the driver on the local host, set this name. We can change this local to some other machines. Okay, and I mean we can say, okay, remove the master. I mean remove the, change it to instead of local. We can actually say it. What do you say? Yarn, and then it will run on yarn. Okay, for now let's just run it locally. Okay, and here we are saying that we're creating the Spark context for 10 minutes 10 seconds window. We will reduce that to 1 second. Okay, we'll reduce that to maybe 2 seconds, and here we are creating a stream on top of SSE in the same way as we have done earlier. Okay, and then doing the word count and printing. Okay, problem is same, just the sources have changed. Okay, the other thing which we are doing is instead of using the Spark Summit, instead of using the interactive one, we are going to use Spark Summit. All right, so now we're going to compile it. All right, also the instructions are also available in readme.md. Why is it taking so much time? Let me just see what is there in the readme.md. It says that run sbt package and then run this kind of command. All right, so you already have this Spark streaming Kafka assembly. Okay, and then you run this command. All right, what does it say? It says that this does not exist. Okay, so project, right, I think we need to recompile it. SBT package, and then we will run it again. Okay, a question from Thomas. What makes map test 5? It basically we are creating a default map with a key called test and value as 5. All right, so you can try running it in the same way. All right, so it's built now. Let me submit it. Submitting means listening to the port, listening to Kafka, reading from Kafka, and processing it. Okay. All right. So it's printing the work. It's printing every second, every 2 seconds it will print. All right. So it's doing the job. And let's also see that which port is it working on. All right. So let me just check in the Spark Kafka. If you take a look at, say, Kafka word count program, it's basically doing nothing here. So I'm just passing some random data as map as the argument. It's not really required. Okay. So here, the more important parts are these. This is just random, so we can ignore this part. And here we are saying that listen to the Spark, and also, sorry, here let's say we are saying create a stream for this. Okay, from this port, then from this group. I got it. Now what does it mean? You know what does it mean? It means that listen from uh what do you call, mm, so Kafka contains many kind of sub queues. Okay, we call them topic. Kafka has many topics, and because Kafka is used organizationally wide, is used by many people in the organization, therefore it has many topics. So people talk on topics, people listen on topics. Okay, so here we are using a topic called test. All right, here we are using topic called test, and And we are saying that pick the second value from this map. Okay. All right. I don't know what does it mean, but okay. So once this thing is created, we are saying that pick the second tuple from that. All right. Second value from the tuple. Okay. Now that this one is running parallelly on one end. Okay. And now let's try to do some more things. This is okay. This is the same thing what we had done. All right. Now on the other side, we are going to create another terminal and export these variables. What does it mean? We're basically going to talk to Kafka broker, and we're going to create this topic called, let's say, topic called test, because test is what we are passing there. Okay. And let's take a look at, okay, the topic already exists, so we don't have to worry about creating it again. So here the topic already exists. You can create your own topic. Instead of test, you can have something else, but accordingly you will have to change the Scala program and build it again. And once you're done with that, you can get the brokers list from Zookeeper. Let's take a look at Zookeeper client. Okay, and get the brokers list. All right. From the brokers list, you can see that there are so many brokers available on Zookeeper. Okay. So from Zookeeper, we are able to find out who are the various brokers of Kafka. Kafka has brokers, as in every node there will be something running, some client which will be handling the Kafka work, and as in some process which will be handling Kafka work on every node. And using that, we found out that this is our broker. Okay, let's see. Let's try to produce something. Okay, let's try to produce something on this. Okay, did it give something this time? No, it did not give anything. All right, what if we pass the data to, okay, so what error are we getting? It's saying that, all right, it looks like that particular node is dead. And let me just kill it. PS3. All right. PS3. Who am I? PS3 minus U. Okay, so this one I can kill safely here. This particular program. Kill -9. Right, so I've killed the process that I started. So what does it mean? Let's again take a look at Zookeeper client. So basic problem is that while our general process works fine, it's just the producer needs the Zookeeper, I mean the actual brokers list. Okay, so to find out the actual brokers list instead of just the Zookeeper, we are trying to find that out. So it says that these are the ones that are up. Okay, so we will use those. All right, let me just test this one with this. Again, you're getting error handling the batch of 200 events. All right, it's not actually picking it up. Let me again find out my process. So looks like this is the process which is the parent of PS3, and let me kill it. Okay, so let me figure it out. It says that error handling in the batch of 4 events failed to send messages after 3 tries. Basically, it's a host problem, and that is the reason. Let's just check if there is anybody at this particular IP address. So Thomas, on which host are you? So it's a dummy kind of a default script which comes with the Kafka for producing the output. All right. I think yes. Let me also try the same thing. Okay, let me try the same thing. Let me, yeah, I think this topic has been kind of marked for deletion. So let me open it and change the topic to from test to say test underscore 5 November. Okay, so let's create SBT package and then let's also create the topic. So here I've created the topic, right? And then let's list it. Okay, so what did I do? Yes, it is there. And then I will start producing to it. Okay, so we are trying to create the producer. Okay, let's just test if it is saving some data to this topic. Looks like yes, this time we are not getting any error. And so let's just try running our program again. So all we did was whatever the program we have left as such, just that we have used a different topic. Okay, in this try, that's what we are trying to do. Yes, so now you can see that it is counting correctly. Okay, and if we say yes command and we pipe the result to Kafka, then we will get far more number of Ys per second. Okay. Also in the code, we could also write uh, to turn off the verbosity, and it'll be better. So Anup's question is, can we check the health of Kafka nodes in Ambari? In Ambari, it just shows that which nodes are running Kafka, and that's it. It doesn't show in detail. I think Ambari has their own UI. All right. So all of you try to just mimic whatever is there. By the by the time you finish, you will have a thought clarity on it. Sixth question is, can you please explain Kafka again? Kafka is a queue to which you can write data and you can read data from. Okay. So just that while talking, we need to specify a topic, as in the producer need to tell which topic they are talking on. Consumers need to consume from a particular topic. All right. Okay, so that's pretty much for Spark streaming. So you can run this in the background, okay, by sending the results to some devnull, and it'll show you the results on the screen. Okay. All right. So similar to whatever we have on Spark, the D stream also provides you the functions like map, flat map, filter, repartition, because it will internally delegate it to the RDD. Okay, it's basically a wrapper because it gets executed on temporarily created RDD. Therefore, it basically delegate all kinds of functions to the parent, to the RDD. Okay, so it has provided all kinds of functions similar to RDD plus some more. One is called update state by key. Okay, so since this script is getting executed for every temporary batch, right? In case you want to accumulate the result, let's say you want to count number of vowels, or let's say you are tracking a particular key that you want to keep updating. Let's say how many words till the since morning have you counted so far. In those cases, you can use update state by key to keep on updating for each key. All right. So this update state by key is quite useful. And all right. Sometimes you may want to combine multiple nodes together, multiple results of the RDD together, D stream together. In those cases, you can use window operations such as reduce by key and window. All right. You have join operations on D streams, just like normal ones. You can save the results into HDFS, and you can also save the result in a folder. When you say save the results a text file, it's going to basically keep on creating the files in HDFS with the prefix that you provide and the suffix that you provide with the timestamp. Okay, so that's what it does. And all right, so you also have functions like for each on RDD. This function will be run on the entire RDD for each D stream. Okay, so this was our quick introduction to Spark streaming. All right, now I think after this assignment, after you have been successfully able to run this, you should be able to build this entire project. All right, you should be able to build this entire project. All right, so that was our Spark streaming. We are left with only two topics now. Okay, machine learning, graph. We are left with actually four topics: machine learning, GraphX, Spark R, and Spark SQL. These are small topics because we won't go into the depth. So we would require 2 more hours. Okay, we would require 2 more hours. And should we do it tomorrow or on day after tomorrow on Tuesday? We can take 1 hour each day, tomorrow 1 hour and day after tomorrow 1 hour. Because the weekend is impossible. Everybody has said no to us. All the students probably because there is a holidays. Yes, Anup, Barsa, Karthik, Kush, Manjunath, Nada, Nitin, Omkar, Prashant, Priya, Ramana. Okay. Same time tomorrow. Yes, we can start a little early, definitely. So we can do it like later will be, yeah, I'm okay with the later as well. But later will be too late for the people who are from India. Or I can do 1 hour tomorrow and 1 hour day after tomorrow. Okay. If 2 hours is difficult on a working day. Thomas, do you suggest a time? All right. All right. Let's do that on Tuesday, Wednesday then. Okay. Looks, I think everybody is fine with the, let's say Tuesday, Wednesday, each day 1 hour. Okay. 1 hour Tuesday, Wednesday. All right. And same time or 1 hour before or 1 hour later? Okay. So right now it's 8 p.m. IST. Okay. Our usual classes are 8 p.m. to this one. This is our usual class. Okay. We can keep it say 7 p.m. IST to 8 p.m. IST. Tuesday, Wednesday. All right. Is everybody okay? Only okay. So okay, for Kush it will be difficult. Kush and Manjunath. All right, let me just try to figure out. How to get it done properly, because I need to solve this. And 24 is definitely no, because people are going on vacation and it's going to be difficult. But let me try to see if we can. Okay, so one is this Monday, Tuesday, 8 p.m. to 10 p.m. How many are okay? Sorry, 8 p.m. to 9 p.m. So, okay. So Sundar, what will be good time for you? 7 to 8, 1 hour before. All right. All right. So let's do it on. Okay. Okay. That's yeah, it'll be recorded definitely. So Tuesday plus Wednesday, because tomorrow is going to be hard for me. Okay. So we'll keep it 7 p.m. IST to 8 p.m. IST on Tuesday and Wednesday. Okay, Kush, we can have one-on-one, and if you have a doubt, we can have that clear. Okay. So for Kush, I'll keep a separate one-on-one. Okay, and this is okay, right, Sundar? Tuesday, Wednesday, 7 p.m. to 8 p.m. Monday is hard for me, and okay. Let's close it with Tuesday, Wednesday, 7 p.m. to 8 p.m. IST, which is 1 hour before than our usual time. Okay, this is 1 hour before. Okay, then see you day after tomorrow, and definitely try the streaming part. Create your own topic and change the code a bit by replacing test with something else, and then run it. And let's catch up on Tuesday and Wednesday. Yes, yes, we'll discuss the projects then. Okay, try the things whatever we have discussed so far, and all right. Thank you very much, and we will discuss rest on Tuesday. Thank you, Priya. Thank you, Sundar. Thank you, Karthik. Thank you, Seek. Thank you, Anupam. Thank you, Saptrishi. All right. See you Tuesday and Wednesday. Thank you, Stephanie. Thank you, Prasant. Have a great day ahead. All right. Bye bye. Have a great day.